guys, welcome to my YouTube channel. Before everything, I wanted to ask you, please like and subscribe to my channel, and don't forget to press the bell button in order to get video updates. In this session, we are going to talk about fully connected neural networks in Pytorch, how to write a deep neural network in Pytorch. And to start with, we will start from fully connected neural networks. In order to train a deep neural network in Pytorch, we must take some steps. First of all, we must define our model. In order to define our model, we must write the corresponding class, and then we must define our dataset and our Dataloader. The datasets and Dataloader was fully discussed in the previous sessions. I talked about how to write a dataset class, how to define your custom dataset, and how to iterate over your dataset by using Dataloader class, a Dataloader object. Then you must define a loss function. A loss function tells you how far your target, how far the output of your neural network, your deep neural network, is from the target values. So you must define a loss function. Different loss functions exist, including mean square error, mean absolute error, binary cross entropy, and these are different loss functions that are used to train deep neural networks. And then you must define an optimizer to optimize and to find the optimum values and the optimum parameter values for your network. And in order to do this, there are different optimizers, and the most famous ones are Adam optimizer and STPS gradient descent optimizer. Then you must try and train your model over your dataset. So you must iterate over your dataset, and in each epoch and each iteration, you must train your model to go through the optimum values. And after some iterations, after some epochs, your model will be trained, and then you will use your model to validate that or to test it with your test dataset. First, we are going to talk about how to define our model. In order to define our model, we must use you must use a class. We must write our model class, which is inherited from nn.module. And nn.module is a base class for all of the neural networks written in Pytorch. Then you must use the init function to initiate, which is the initialize function to initiate the neural network. This is something that this function is called whenever you are just constructing an object from the class. This is something that you do for defining each class in each coding language. And in your initial function, you must define different layers of the network. For example, if you have a fully connected neural network, and this fully connected neural network is consisted of one input layer and different hidden layers, you will define the different hidden layers, the number of the hidden layers, and number of the nodes each hidden layer has in this part. And then there is a forward function, which is actually the method of the nn.module class, which is the base class we use, and you must rewrite it in order to do the actual message passing and do the actual computation of your neural network. Whenever you call an object initiated from your model, then and whenever the input is passed to this object, then this function, the forward function, is called. This is something that we must do. So here we will write a class. For example, a name. We will define a name for our class. Here I have defined my model class. The name for my class is my model, and it has been inherited from nn.module. So as you can see, nn.module is the base class for the class of my model. And then I must use the initialization function. So I use def init. And in def init, I have some input arguments. First of all is self, which refers to the self object, to the self class. And then you must use some arguments. For example, here I have defined number of the nodes, input nodes, number of the output nodes, and number of the hidden layers that I use. For example, or you can use other different input arguments as well. So in this section, and then after that, you must just initialize your super function. I mean, the master, the parent function as well. And then you will rewrite the forward function. The forward function takes any input and then makes some computations over the input, and then will return an output. This is something that is called whenever you use call an object initiate an object constructed from a class. For fully connected model, for actually a fully connected model that we are going to talk about, we have we must use nn.linear. You know, nn is a module from Pytorch. You can import nn module by using import pytorch.nn, and then from the nn, which is abbreviated for and stands for neural network. NN stands for neural network. So from the NN you have different modules, different classes from the NN module. One of the classes is linear class. And in Pytorch, NN that linear applies a linear transformation on the input data. For example, here you have input data which has 4 features, and then you will use a linear transformation in order to transfer in this data into 3 dimensions. And to do that, you will have a matrix. You will have a 3x4 matrix. As you can see, W1 is constructed from 4 weights, which are, for example, the blue part, which actually transforms the input data into all of the input data into A1, and W1 to W4 here for W2 are the weights which are indicated, illustrated by green lines, and they transform our input to A2. And the same thing is for A3. And when we put these weights in a matrix, in a row matrix, we will have a 3x4 weight matrix. This is the weight matrix, and this weight matrix, which is W transform, is multiplied. I mean, the matrix multiplication by our observation matrix. The observation matrix is constructed by putting the different observations vertically in the columns of the matrix. And as you can see, x1 to x4 stands for 4 features of the of observation 1. Then the same thing is true for observation 2, 3, and 4. And then we will use some bias. And here, as you can see, this is a linear function. So nn.linear will do this linear function, is defined to make this linear function. And this linear function is W transform x plus b. B is the bias, and W is the Lerner weights. And W and B, as you can see, are the Lerner parameters. Here we have 3x4, it means 12 parameters here, and 3 parameters for bias. So we have 15 Lerner parameters that can be learned from this small linear transformation. So in order to define this linear transformation, we will use the linear class from the NN module, nn.linear. nn.linear will take one input and one output. Input is number of the input nodes, and output is the number of output nodes. For example, here, number of the input nodes are 4, and number of the output nodes are 3. So this is the, you must initiate this class, I mean construct an object from this class, and define that as a self-attribute of your actually model, of your model. So you can access to this layer 1, which is the linear function, in your forward, because it's a object variable, and you can access this because you have defined it as self.layer1. So here in the forward function, you will call self.layer1 of the input. So whenever you give an input, and for example, the input is, for example, here you have a 4x4 input observation input, then the output will be something like a 3x4 output observation matrix. So the number of the features will be changed by this linear transformation. This is the base for a fully connected model. And as you know, there are different, here if we use a linear transformation, we cannot learn any nonlinear function. So we know that in a hyperplane, for example, in a hyperspace, you have a lot of features that are not linearly separable, and you must use some nonlinear functions. So in order to learn nonlinear function, you must use some activation functions that make our linear function nonlinear. And there are different activation functions that we are going to talk about. there are different activation functions that can be used in our network. One of them is sigmoid loss function. In sigmoid loss function, the formula for sigmoid loss function is this, and it will just it will take the input and just will limit the input between 0 and 1. So if you have minus infinite, you will have 0, and if you have, for example, plus infinite, you will have the output of 1. And we have actually ReLU function, which is the rectified linear unit, which is just a ramp function. As you can see, for the negative values it gives you 0 value, for the positive values it gives you the same, it gives you exactly what it takes as the input for your output. And this works as a gate function, so each negative value that comes to this function will become 0, and each positive value that comes into this function will become without being changed. There is another loss function which is leaky ReLU, which is not as strict as ReLU, so it doesn't really make every negative value to get 0, and instead of that it will give you 0 values with a slight slope, that the slope can be adjusted by you, and in most of the cases the slope is 0.1 in negative values, and for positive values it will be some of the actually slope will be 1. The next thing that we have to do is to use a stack of these linear functions, these linear transforms, and after this linear transform we use an activation function, but we must use a stack of hidden layers, not just one hidden layer, not just a one input and output layer. We must use some hidden layers, so we have very complex functions and very complex non-linear hyperplanes in the hyperspace, so that our instances will be discriminated. Our instances can be recognized between different classes, and we can discriminate between different classes very well. So we use different linear functions. For example, here I have used a linear function, so it gets the number of the input nodes and will give you number of hidden nodes, the first value of the number of hidden. For example, number of hidden here can be a string or a tuple. For example, if you have 2 hidden layers, the first one can be it is a tuple of 2 values. The first one is 5 and the second one is 5 as well, for example here. So the first one is 5, the input nodes here is 5 to 5, so it is a linear function which will transfer your function, transfer your input features into an output space with 5 features, and then you will use your activation function. So you will define nn.ReLU as your activation function. Then you will have another layer, and all of these layers are just define your initialization function. So in the next linear layer you will have number of the hidden of zeros, which is 5, and the number of hidden of 1, which is 5, for example here, and you will have a transformation between 5 and 5. So the number of the input features will be 5, number of output features will be 5. Then you will have another ReLU, which will just make some nonlinear transformation on your data, and then you will have another linear function which maps your second hidden layer into output nodes. And then in the last you will have, for example, an activation function, something like, for example, sigmoid function, or you can use no activation function for this part. And as you can see in the forward part, you can just call each of these attributes, each of these objects. So for example here, for example, self.layer1 will make a linear transformation input, and then self.activation will make it non-linear, will apply the activation function on it, and then the output will be outputted, and then the output variable will be given to the layer 2, the second layer, and the activation function will be applied on it, and the output will be just given to us, and the output will be given to the, for example, layer 3, and the final output will be constructed. Here we can use activation function, or we cannot. It depends on our application, our loss function. This is something that we must define in our network. And we can have different layers. For example, you can have, here we have used 2 hidden layers, but we can define as many as hidden layers that we want here in order to transform our input to the output function. In the next level, in the next step, you must define your data set and data load. This is something that we talked about in the previous sessions. I talked how to define your custom data set class and how to use the preloaded data sets in Pytorch. Here we used, for example, the MNIST data set, which is a preloaded data set. The data sets, as I said to you, is a module that is that we can import it by import utils.data.dataset, and then from this util we have a MNIST class, and we have called the MNIST class. We said that we want to download the data, and then we want to transform our input image to tensor, and I have used train equal to true here, because here for I think MNIST data set we have about 10,000 number of images for test and 50,000 number of image for train. So it will assign the train functions a data set for this train image. So I want to make a data set from our train image. And here I use a data loader class in order to iterate over my data set. So I will make an object from this data loader, and I will use shuffle equal to true. And for the test data set, I can make shuffle. I will do the same thing, but here there is something wrong. I must make it true. For example, here train will be false because this is my test, and for shuffle I must use false. So as you can see, we have for a test data set we will equal train equal to false, so that the train data set object will be constructed from the MNIST train data image, and then I use a data loader class, and I initiate the data loader class. I will use the data set object in my in order to construct a data loader object from my data loader class, and I will equal the shuffle I will put shuffle equal to false in order, because I don't need to actually scramble the image in my test data set. In train data set, whenever I want to train my model, I will shuffle in my data in each epoch, but in the test, whenever I want to test my model, there is no need to do that. And in order to, if you don't know how to define your data set, how to use the data loaders, you can watch the videos from the previous links. I will put it in this presentation. I will put my presentation below the video. You can download it and you can look at it. I will make a PDF version from this presentation. I will put the link below. You can easily download it and look at it, and then if you like, you can see the dataset and data loader videos from the previous sessions as well. Then we must define the next step. We must define a loss function. So a loss function tells us how far our algorithm is our model is from realizing the expected outcome. We expect a target value, but we will give something. We will have a prediction which is in the first steps of training far from our target values, and we want to make the prediction as close as possible to the target values. So we use a loss function. For example, we have an image here. We want our image to be something, another image, and we have a target image here. We will use a mean square error in order to find the error between the square of the error between the target value and the predicted output. Or for example, in a binary class, for example, in a classification problem, you can use binary, which is a binary classification. You can use binary cross entropy loss. So there are different loss functions you can define, depends on your application. There are some, but in NN module, in neural network module of Pytorch, there are some defined loss function you can use them. For example, for mean square error loss, we have nn.mse loss, which is a class that you can make an object from this class and use this object. For example, mean absolute error or norm 1 error, you have nn.l1 loss, and for cross entropy, you have nn.cross entropy between the input logits and the target. But for the binary cross entropy, you can use nn.bce, which stands for binary cross entropy loss function. And you can use also BCE with logits loss, which combines a sigmoid layer with the BCE loss in one single class. For example, it applies a sigmoid function on each of the output logits, and then it will apply a binary cross loss on each between the output that is transformed by the sigmoid function and the target values that you give to it. So these are the different things, different objects that you can, different classes that you can initiate, construct an object from them and use them. And then in the fourth step, you must define an optimizer. In order to use an optimizer, you have a module which is optim. From the torch.optim, you have a package implementing various optimization algorithms. For example, for steepest gradient descent, you have optim.sgd, which takes the parameters of your network and the learning rate, and it will make an optimization object out of this class. And you can use optim.adam for Adam optimization too. It will take the parameters of your network and the learning rate, and then the betas, which are the momentum for your Adam optimizer. So in order to do this, we must just, for example here, first I initiate my model. As you saw, my model here is the class that I use. Is the actually neural network class, which was inherited from the nn module, and I wrote it in the previous slides. And then I will initiate this class. I will make an object, create an object from this class. I will give our input arguments into that. For example, here, the input nodes I have defined, for input nodes I have defined 28 by 28 input nodes. Why? Because in this example, I want to classify MNIST image, and in MNIST image, each image has 28 rows and 28 columns, so I will flatten each image, and each image will have 28 by 28, which is equal to 784 actually nodes as the input node. And my output node will be 10, because I will have 10 outputs. One of them is for 0, one of them for 1, and it is the one hot vector that is for the output. For example, here I will have 10 outputs. One of them is supposed to be 1. If the first one will be 1, it will stand for 0. If the second one will stand that the input is classified as 1, digit 1, and here it stands, when the third one is 1, it stands that the input image is 2. So it will give us the output. So here, as you can see, number of the inputs is 28 by 28, number of the output nodes is 10, and number of the hidden nodes are, for example, here I used 512 and 128 hidden nodes for 2 hidden layers. So I used 2 hidden layers, and each hidden layer, the first hidden layer will have 512, and the second hidden layer will have 128 number of nodes. Then I can use .CUDA in order to make it to transfer it into GPU. I will just this is something that I will teach in the next session, so I will omit this. Okay, and then I will take the parameters of my network. This is the object network that is constructed from my model class. I will take the parameters. I will get it by using the parameters method, and the parameters are extracted, and I will use optim.sgd, which is the stochastic gradient descent, and I will give I will have 2 input arguments. One of them is params, that I will put it to parameters that are extracted, that is calculated here, and then I will use learning rate equal to something reasonable. Here, for example, for this application, learning rate can be 0.01 for this application. If you put learning rate a high value, your network will not reach an optimum value, and it will just fluctuate over the optimum point. And if you put it as a very low value, it will not decrease the optimizer will not go toward the optimization very fast, and it will take a lot of epochs and a lot of iterations in order for your network to go toward the optimization point, optimum point. And then the next step, you must train your model over your data set. You must iterate over your data set and use a forward pass in each iteration. So in order to do this, here you can see define a for loop for number of epochs. For example, here number of epochs is, for example, epochs is 100, and and I have used a loop for number of the epochs, and then I use another loop, and in the next loop I use enumerated over my train data loader. So when this loop finishes, one epoch is finished. So these two for functions will iterate over my data sets for number of the epochs times. For example, if number of epochs is 100, it will iterate over on my data set for 100 times. And because my train data loader is shuffled, as you saw when I constructed an object from this train data loader, you saw that I use shuffle equal to true. So in each epoch, the training data loader will shuffle the data and iterate over my over my data set. So in each iteration, the data is equal to image and label is the tuple. The first one, image, is the tensor, is my tensor, input tensor. The second one here, the label will be the label of these images. For example, here if I have a batch, for example, a 32 batch of images, I will have a batch of 32 labels here, and each label stands the number that this written image, this handwritten image belongs to. For example, number is, the digits are 0 to 9. So I will have 10 unique labels, and each of the image is associated, is assigned with a label. So I will get the image and the label, and then I see that each image is accompanied with a label. A label is a digit, as integer number. For example, for an image, I will have, for example, even the handwritten image is 0. I will have the label is 0, an integer 0. But in the output, I will have a one-hot vector, because I will have 10. As you saw, I will have here, I will have 10 outputs. So I must use one-hot encoding here to encode this integer value as my label into a one-hot label. In order to, for example, here you see for example, 5 is one-hot encoded into 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Or for example, 0 is, the first one is 1 and the rest are 0. For 4, the fifth one is 1 and the rest are 0. For the 1, the second one is 1 and the rest are 0. So it is the one-hot vector, one-hot encoding, and we must use one-hot encoding to encode my labels into a one-hot encode vector. So to do this, I will use function .one-hot encode. It takes our label and number of the features in the output one-hot vector that we want. And in order to use the one-hot function, we must use torch.nn.function, and which is functional, which has a number of very useful and helpful functions. So whenever you want to do some mathematical operations on your tensor, you can use nn.function as well as here. So then you will have a target value. For example, if you have for example, 32 images, then you will have 32, a matrix, a tensor, which has 32 rows and 10 columns, and each column represents one of the values of each column is 1 and the rest is 0. So then in the next step, you must give your image to your network, and in order to do it, you must make your image, flatten your image, and in order to flatten your image, you must use view function. So it will you will say to this function that I want, for example, 32, a batch of size 32, and the rest of the columns you must calculate how many columns that I have, and it will give you 784 number of columns, because each image is flattened into 784 number of columns. Here I must do some modifications. Here I don't want to talk about CUDA and how to transfer your data into CUDA function into actually GPU, so I will not use CUDA for now. And then you will call your network and you will feed your image tensor into your network, and then the output will be calculated. This is the forward pass, and you will just give the output the output tensor and the target value that you want here. The target value is the one hot encoded vector, and you will use the BCE loss object which has been defined in the previous section. What was that? Here, as you can see, it was in this section you use the loss function. For example, here your loss function is, for example, n dot binary cross entropy. So here you will use this the object that's constructed from that binary cross entropy loss, and then you will calculate the loss. Here the loss has all the records of all the calculations that has taken place, that has been done in all the parts of your network in different network layers. So if you back propagate over it, it will have the graph of the network, so it will do the back propagation step by step. So this is the forward step, which you only calculate the output, and you just, in a forward path, you give the input to the network and take the output and take the loss function. In this next step, you must backward over your network and use back propagation and optimize your network parameters. In order to do this, you must use a backward, you first must use the zero grad method for your optimizer in order to make all of the gradients, accumulated gradients in the previous steps of your optimizer to get zero, and then you must call the backward method of your loss, which is your loss here is, for example, here is the output that you will, the loss, for example, here is it is one dimension, it is the mean square loss, or here is binary cross entropy loss. But because it has all the network operations in it, and the graph of the network is recorded, so whenever you backward over it, it will make a backward propagation, and then whenever you use the optimizer dot step, your network parameters are optimized based on the optimization algorithm that you use. For example, if you use steepest gradient descent, it will just use the gradients, the gradient values in order to fine-tune the network parameters and will adjust the network parameters in this step. So now it's time to go through the implementation steps again and to see what are our results in any IDE that you want to use. Here I use Pytorch. You can see the results here, and I will go through the implementation steps again, and then I will talk about the results and how it works and how many epochs that does it really need to be trained. So here you can see that I have imported the necessary modules. Here I have torch.transforms. I have imported from the torch.transforms the two-tensor class, which actually transforms each image, a PIL image or a NumPy image, into a tensor, which is used in my MNIST dataset. I will use this transformer and this transform to transform each of the MNIST dataset image to a tensor image. And then I have imported datasets from the Torch Vision in order to this module has a lot of datasets, preloaded datasets, some such as MNIST and the other datasets, and I just, in order to construct an object from the MNIST dataset, I must use datasets module and just use this datasets module to make an object from this dataset. And then I have used Dataloader, imported Dataloader, imported neural network, I have imported optimization module, I have imported functional, neural network dot functional, which I can use it for doing applying some functional, some mathematical functions on different tensors. I have imported Torch as well. So I have written my model class. The model class is inherited from the nn.module, which is the base module for all of the neural network modules in Pytorch. And then in the init function, I have defined different layers. Here I have 3 linear layers. The first one is the input layer. Then I will have 2 hidden layers. And then I have also defined different activation functions. I have the sigmoid activation function as well. And then I used in the forward function, I have rewritten the forward function. So the input will be actually fed into different layers, and the output is calculated and returned from my class. Then I defined an evaluate function that I will talk about that later. And then I have defined my dataset and data loader for the train and test. And the batch size here, I have defined 32 as the batch size. And then let me modify this, because yeah, I want my test dataset to be downloaded in test underline data root function folder, and my train dataset to be downloaded in train underline data root. And then from my model class that I have defined here, I have constructed an object from this model, and the object is in a, and then I have given some input arguments to it. I talked about that. And then I will clear the CUDA function, because it's something that I'm going to talk about in previous section, in the next sessions. And then I have just defined the parameters of the network. I have just taken the parameter of the network, and I fed these parameters to the SGD class, and I constructed an object from the SGD class. And then I constructed a object from the NN dot binary crash entropy with logits loss as for calculating the loss function in this example. I think here I have not using the sigmoid function. I think, yeah, I can delete this activation function. Sorry, it was something that I must modify, because this activation function is we don't need this, because the binary cross entropy with logits loss will do exactly the same thing. It will apply a sigmoid function on the output, and then will calculate the binary cross entropy. If, for example, I use the binary cross entropy here, for example, binary cross entropy loss, then I need the output function, I need the sigmoid function here, and the sigmoid function will be applied in the output. But here I have not applied the sigmoid function on the output, because this loss function has the this sigmoid function in itself. So I will not apply the sigmoid function again here. So, and then I will define number of epochs. For example, here I define number of epochs equal to 100, and then I have used two for loops on my data. One of them is on number of the epochs, and the other is the for loop on the enumeration of your train data. So it will enumerate over your train data, and in each iteration, a batch of the data, a batch of the labels are just fed, are just outputted, and then I will here I have used the label here to make it as a one-hot vector, and I have just encoded it to a one-hot encoded vector. And then matrix here is matrix, because it's a batch of data. And then here I have, just as I said, I have flattened my image, and I will delete this CUDA parts, because I don't want it to be implemented in GPU. In the next sessions I will talk about GPU, but now I want it to be implemented in CPU. Then I will do the forward passing this section. The image is forward passed into the network, the output is calculated, the binary cross entropy is calculated here, and then I will backward over this loss function, and I will step over the optimizer, and the optimizer will optimize my network parameters one step. And then here I use loss.item, which will actually forget about the graph of the network, and it will just give the value of the loss. And I have just got the value of the loss by loss.item, and this value is just summarized over different batch in different iterations, and in the average loss actually here we see AVG on the loss variable. And then after each 100 iteration, after each 100 iteration, I will calculate the average because it was summarized all of the 100 iteration, and then I will divide it by 100, and it will become the mean value, I mean the average value, and I will just append it to my training loss list. So I will have the loss functions in a list, stacked in a list, and I will show it later. And here I just printed the loss value, the mean square loss value, and the number of the epochs that have been passed, and number of the iteration that have been passed. You can see this. And then after each epoch is finished, as you can see, this line is epoch is finished here. One epoch is finished. Then after finishing each epoch, I will evaluate my network, the output of my network over my test data loader. So this is the function that I use to show the evaluation process. You can see the function evaluate is defined here. So in this function, I will enumerate over test data loader here, and for each test image, I will do the same thing. I will give it to my network, and then the output I will give it to my network, and the output. Then the output will be something, for example, if I have a batch of 32 images, the output will be a matrix 32 by 10 because it is one hot encoded. I will find the maximum value by argmax. I will see which elements, which column for each row, which column has the maximum value, and this is corresponding to the label of the image. So because of that, I will find the argmax of the output, and I will see which of my labels are equal, the true labels are equal to my output, and then this will give me a mask constructed from true and false. For example, if all of the 32 images of the batch are classified as correctly, then the mask will be true, and 32 truths. And then when I summarize over the mask, I will have 32 truths, 32 ones, and then the batch size is 32 by 32 will be 1, the accuracy will be 1. So the accuracy is just summarized in each iteration, and then after all the iterations are finished, I will find the final accuracy by averaging over all the accuracies that has been calculated. I will retain the accuracy over my test data set here. So this is the thing that is done in the evaluate function, and after each step, the accuracy is just appended to the test accuracy list, so that in the next after finishing the training, I will just show it. I can plot it. So here, in order to plot it, I used these two lists. One of this lists was train loss list, which was the mean square loss in the training phase, and the other is test accuracy list, which is a list of accuracy over the test data set. And I will use NP, which is numpy here, numpy as array, which will transform it into a numpy array. So the numpy array can be plotted by matplotlib. So I imported matplotlib.pyplot as PLT, and then I plotted each of these, as you can see, each of these arrays. So let me run this code. Here I will put number of epochs equal to 3 in order to finish the training process very soon, and to see the results and plot the results very soon after finishing the training process. In the next sessions, I will talk how you can plot your loss functions in real time by using the tensor board. But here, because I have not talked about tensor board and how to show the network values and the network loss function values over time by using and how to use tensor board to show them, I have used this technique in order to show them. So I used some tensors to store, some lists to store these loss functions or these accuracy function, and then after the training process is finished, I will show them through the plot function. So let's see what will the result be. Here, as you can see, the training process is started. The loss function is increased through each iteration. One iteration is finished, so we will go to epoch, the next epoch, and the accuracy will be 50%. around 50%. Then the accuracy is, in the second epoch, the accuracy is increased. It will be 67%. Then the accuracy is again increased. And let's see, okay, here are the results. Because the number of epochs is very small, you will not see very smooth functions, but in the next sessions when I talk about tensors, you will see smooth functions over time. So here, as you can see, the binary cross entropy loss is decreasing through the epochs, and here the test accuracy is increased through different epochs as well. So this is the codes. This is how we implement deep neural networks in Pytorch, and the simplest one are the linear layers, and by stacking different linear layers and using non-linear activation functions, we can define fully connected neural networks. And by fully connected neural networks, we can define different complex functions in the hyperspace to discriminate between different samples or belonging to different classes. So this is the whole thing. In the next sessions, I'm going to talk about CNN networks, how to implement convolution neural networks in Pytorch, and then in the following other sections, I'm going to talk about more complex neural networks, how to define these models, and we can see that that's not the base is completely the thing that I taught you today, but it has the same base, but it will be a little bit more complex. Thank you very much. Have a good day and goodbye.